Hello students, in the previous video of vapor power cycle, we discussed briefly about regenerative cycle, and today we discuss about a numerical based on regenerative cycle. So here is the question. In a single heater regenerative cycle, the steam enters the turbine at 30 bar 400 degrees Celsius and the exhaust pressure is 0.1 bar. The feed water heater is a direct contact type which operates at 5 bar. Find efficiency and the steam rate of the cycle and the increase in mean temperature of heat addition, efficiency and steam rate as compared to the Rankine cycle without regeneration. Neglect pump work. So here for single reheater regenerative cycle, we draw the schematic diagram of the steam power plant, and this is the TS and HS diagram according to the given question. So here as per the single heater regenerative cycle, so this is the boiler, turbine, condenser, but from this turbine the total mass is not entering to the condenser, some mass is fed to this heater, that is mkg. So the mass which is entering to the condenser is 1 minus mkg. So this 1 minus mkg is entering to the condenser and that is fed by this pump to this heater, and there this 1 minus mkg is added with this mkg and this total mass becomes 1 kg here, and this is fed to the boiler by means of this pump. So according to this, here the TS and HS diagram we have drawn. So according to the question, the datas are the initial pressure, the first pressure that where the heat addition will take place, that is at 30 bar. Second pressure with which the mass mkg is added to the heater, that is at 5 bar, and the exhaust pressure of the turbine, here it is considered to be 0.1 bar. So this is considered here P1, P2 and this is P3, right? So for these questions, here we are going to calculate the efficiency, steam rate and mean temperature with regeneration and without regeneration. So first we are going to calculate with regeneration, then we calculate without regeneration. So for with regeneration, this is the schematic diagram, and here are how many states we have considered here, that is 1, 2, 3, 4, 5, 6, 7. For these 7 states, we have to calculate the enthalpies. By considering enthalpies, we write down the expressions of efficiency, we write down the expressions of steam rate, we write down the expressions of, that is, mean temperature. So first we calculate H1. So for H1, we have to prove that this state is in superheated regions. See here I know from the calculation that this value, this state lies in the superheated region. That's why I considered here in the superheated region. This I can prove here. See from the steam table. So here we use the steam table. In steam table we have 3 kinds of tables. One is saturated pressure table, saturation temperature table and superheated table. So here you can see the saturation temperature, saturation pressure and superheated temperature. So now first I considered the state 1. I assume the state 1 to be saturated. If this is saturated, so its corresponding temperature is that I consider from the steam table, that is at 30 bar pressure, at 30 bar, see I am considering 30 bar pressure. So where it is? So that is here. So see in this 30 bar pressure, what is its corresponding temperature? 233.90, right? So here it is written that the saturation temperature is 233.90, but the given temperature is 400 degrees Celsius. So it means this saturation temperature is less than this 400 degrees Celsius. So if this is less than 400 degrees Celsius, so if I consider a state 1 to be here the temperature is 233.90, but the given temperature is 400 degrees Celsius. If the given temperature is 400 degrees Celsius, that lies above this, so it means this state is superheated state. So for this state, I have to consider the value of enthalpy, that is H1. So it means we have to see the superheated table. So now see, I have considered the superheated table. So now I am opening the space superheated table. For superheated table, what pressure I have to consider? I have to consider the 30 bar pressure. So 30 bar pressure is opened here. 30 bar pressure page is opened here. For 30 bar, what is the temperature it is given? The temperature is given 400 degrees Celsius. So 400 degrees Celsius. For 400 degrees Celsius, these are the corresponding properties. So for C, the first column is for volume, second column for internal energy, third enthalpy, fourth entropy, and all these properties are specific properties. So see here, simultaneously I consider both H and S value, because both H and S value is required for at every point. So for state 1, enthalpy is 3230.9 and entropy is 6.9212. So see, it is written here. Enthalpy is 3230.9 and entropy is 6.9212 kilojoule per kg Kelvin. This value we get from the steam table. Now see, from this TS diagram, it is a constant entropy line. It means we can say S1 is equal to S2 is equal to S3. So see, here I consider this S1 equal to S2 equal to S3 equal to 6.9212 kilojoule per kg Kelvin. Now for second state, we have to consider the enthalpy H2. So see, again I assume this state 2 should lies here. If the state 2 lies here, this is the saturated state. For saturated state, for the state 2, what is the pressure? 5 bar. For 5 bar pressure, what is the value of entropy that we have to consider from the saturated pressure table? So from saturated pressure table, see here I have considered saturated pressure table. This is saturated pressure table. For saturated pressure table, I consider for 5 bar, what is the value of entropy here? See, what is the value of entropy? So this I considered. See, for 5 bar, entropy is Sg is 6.8213, right? 6.8213. So see, here I have written this 6.8213, but this value is less than 6.9212. So this value we already get from S1, that is S1 is equal to S2 equal to S3. So if this is the saturated state, so this value must be equal to this value. But this value is the value of the entropy at the saturated state. So as this is less than 6.9212, so it means if I consider the state to be saturated, here the value must be 6.8213, but the value is 6.9212, which is greater than this. So this must be comes towards right. So if it comes towards right, it means this is the superheated region. That's why the state 2 lies in the superheated region. So here we can prove that as 6.9212 is greater than 6.8213, it means the state 2 lies in superheated region. Right? So see, next we have to find out the enthalpy of state 2. So see, as we prove that the state 2 lies in the superheated region, it means we have to follow the superheated table for the value of enthalpy. So see, for value of enthalpy, we have to consider the 5 bar pressure page for superheated table. So now I consider here But for this 5 bar pressure, what is its corresponding temperature? So is it given in the question? No, it is not given in the question. But we have entropy value for 5 bar pressure for state 2. The pressure is 5 bar, but entropy is what? Entropy is 6.9212. So we have to find out this 6.9212 in 5 bar pressure phase. So see, now I am going to find out where this 6.9212 entropy is given. So here I check this value 6.9212 or approximately the nearest value. So here I can see this is 6.8213, this is 6.8648, 6.9162, 6.9656. So these two values are nearer but not exactly 6.9212. Or you can say this 6.9212 lies in between these two values, right? So if it lies in between these two values, it means its corresponding temperature 6.9212 lies in between these two temperature. Its corresponding enthalpies lies in between these two values. So for this we have to follow the interpolation method. See, for interpolation method we have entropy that is 6.9212 and its nearest value that is 6.9162 and 6.9656. These two value we get from the steam table and it is here 6.9162 and 6.9656, right? So for this corresponding entropies we have to find out corresponding enthalpies and corresponding temperature. So for this we have to follow the interpolation method. So here I have considered this value as SA and this is SC, and the value which we have that is 6.9212 that I consider to be SB. So for this, what is the corresponding what is the corresponding temperature and what is the corresponding enthalpy, that we are going to find out. But for this 6.9162 we have the corresponding temperature, I have the corresponding enthalpy, and for this SC, for this entropy I have the corresponding temperature and corresponding enthalpy. For this we are going to calculate the temperature and enthalpy by using interpolation method. So here is the method. So SC minus SA by SB minus SA equal to TC minus TA by TB minus TA. So I have all the values I have except this TB. So by substituting all the value I get TB value. Similarly I have all the values except this HB. So by substituting all the values I get HB value, right? So H2 is equal to HB now. So H2 equal to 2785.12. This I have to find out. So for state 1, for state 2 enthalpy is over. Now for state 3. Now state 3 lies in the wet region. So the state 3 lies in the wet region. So as it lies in the wet region, so the properties expressed as H3 equal to HF3 plus X3 HF3G FG3 and S3 equal to SF3 plus X3 SFG3. So see, first I use this expression S3. So I know that S1 equal to S2 equal to S3. So that value already we find out 6.9212 equal to 0. And SF3, this value we get from the steam table. For state 3, what is the pressure? For 0.1 bar. For 0.1 bar, I have to find out for 0.1 bar. So see, here it is the 0.1 bar. For 0.1 bar, what are the corresponding properties? So see, this is enthalpy HF, HFG, SF and SFG. These values we will write down from here. HF value 191.83, HFG 2392.8, SF 0.6493 and SFG is 7.5009. See, it is clear. It is considered SF value is 0.6493 and SFG is 7.5009, right? So this value we have to substitute here in these two equations. So we get the value of X3 and H3. So now I use for entropy. So 6.9212 equal to 0.6493 plus x3 into 7.5009. So x3 is this. So substitute this value in this equation, HF value and HFG value from the same table. By substituting this value, H3 equal to 2192 kilojoule per kg. Next is H for state 4. So see here, pump work we have to neglect. It means state 4 and state 5 we consider to be same. So enthalpy of 4 and 5 will be same. So if we get the value of enthalpy for state 4, that we will consider for 5. So 4 is considered to be saturated state at pressure 0.1. At pressure 0.1. So see here, the pressure is 0.1. For 0.1, what is the value of HF? That is 191.83. So 191.83. So this is the value of H4 and this must be equal to H5. This is equal to H5. So for similarly, its corresponding entropy, so that is 0.6493, that is from the steam table. Similarly, for state 6. So for state 6, we consider this is saturated state. So now here, as now pump work we have to neglect as per the question. So 6 and 7 we have to consider the same point. So if we get the enthalpy of 6, we get the enthalpy of 7. So see, for this, what is the pressure? Pressure is considered to be 5 bar. For pressure 5 bar, what are the corresponding properties? So see, here it is 5 bar. So here it is its enthalpy, that is Hg, that is 2748.7, that is kilojoule per kg. So this is consider here. Sorry, this is Hg. So this state is this is for state 6, the state is HF. For state 6 is, this is HF. So for HF, what is the value of enthalpy? That is 640.23. So this is considered here. H6 is 640.23 kilojoule per kg. So this is H6. So H6 is equal to H7. So 640.23. So its corresponding entropy is here. Now we have to calculate the mass. So we have all the enthalpies of every point. So by using those, we can get the efficiency value, steam rate and mean temperature. So before that, we calculate mass, because here the mass is not uniform at every state. The mass, some amount of mass is extracted from the turbine and feed to the heater. So that's why the mass is not uniform. So we have to calculate what is the amount of mass that is extracted from the turbine, that is M. So see, this is the heater. So here state 2 will enter and here state 5 will enter. State 2 is entering with M kg, state 5 is entering with 1 minus M kg, and this is state 6 which is leaving the heater with mass 1 kg. So see, according to this, we write down the equation M into H2 plus 1 minus M into H5 equal to H6. And by rearranging this, we get M equal to H6 minus H5 by H2 minus H5. Already we have this value. By substituting this value, I get M equal to 0.173 kg. Right? So next is Q1. Q1 is H1 minus H7. Q1 is H1 minus, so see, this is the heat addition process. 7 to 1 processes, that is the heat addition process. So H1 minus H7. So H1 minus H7. So I have all these values. So by substituting this, I get this value. Similarly, WT. WT is H1 minus H2 plus 1 minus M into H2 minus H3 into H2 minus H3. Right? So I have all the values. So see, this is the turbine process. So here H1 minus H2 with 1 kg and H2 minus H3 with 1 minus M kg. So it is written here 1 minus M into H2 minus H3. So now efficiency is what? Efficiency with regeneration we are going to calculate. So WT minus WP by Q1, WP is neglected and it is equal to WT by Q1. So after substituting this value, the efficiency is 36.14% and steam rate is 3600 by W net. So this WP is neglected, so it is only WT. 3600 by WT equal to 3600 by this, and we get the value of steam rate to be this. Mean temperature H1 minus H7 by S1 minus S7. So by substituting this, we get the temperature value to be this, but this is we get in Kelvin. So subtract minus or 273.15, you get this value in degree Celsius. Now without regeneration. So if I consider without regeneration, this part we have to omit. So this boiler, turbine, condenser and directly to the boiler by means of a single pump. So if we consider in this way, so this is 1 to 3, 3 to 4, then directly, or 4 to 5, then directly to the 1, right? So if we consider this is without regeneration, so see the mean temperature to be, as it is 5 and 4 to be 1 point, so here it is 4 minus 1, or sorry, that is 1 minus 4, H1 minus H4 by S1 minus S4. But as it is with regeneration, so here we have all these states, so this is H1 minus H7. But as it is without regeneration, this is H1 minus H5, or that is H4. Right? So H1 minus H4 by S1 minus S4. We have all these values, directly we substitute there and we get this value in Kelvin. So minus 273.15 if we do, so we get in degree Celsius. So increase in mean temperature due to regeneration. So this, from this value you have to subtract this. So you get this value, and this is the increase in temperature due to regeneration. Now similarly, we have to find out efficiency and steam rate. So there we have to calculate turbine work without regeneration. If we consider turbine work without regeneration, so if it is without regeneration, this is directly H1 minus H3. So see, here it is H1 minus H3. So we have all these values, substitute here and we get WT. Then steam rate is equal to 3600 by WT minus WP. WP we have to neglect it, so it's only WT, and this value is 3.46 kg per kilowatt hour. Next is increase in steam rate due to regeneration. So see, this is the without regeneration and this value is with regeneration. Just subtract 5 minus 3.46, we get this is the increase in steam rate due to regeneration. Similarly, efficiency. Efficiency is what? That is, directly it is written here, that is WT. So here it is WT H1 minus S3 by Q1. Q1 is H1 minus H4. If it is without regeneration, so the Q1 is directly from this point to this point, so this is H1 minus H4. So by we have all this enthalpy. By substituting this, we get efficiency for without regeneration is this. So if it is without regeneration, now increase in cycle efficiency due to regeneration. So with regeneration, the efficiency is 36.14, and without regeneration, the efficiency is 34.18. By substituting this, just subtract with the two values, we get 1.96%. Thank you.